Hi, it's Mr. Brewer. Do you know what the chemistry teacher's favorite tree is? Anybody? But of course, it's the stoichiometry. Boom, boom, Okay, all kidding aside, look, today's lesson is going to come to you from the war room once again. And our lesson today is on what we call stoichiometry. So let's get right down to it. Let's get rid of my face here so we can focus a little bit better about what we're doing. Stoichiometry happens to be a mathematical idea. That's actually, if we were going to look at a textbook definition, it might say something to this effect. It might say that it is the mathematical relationship between reactants and products of any chemical reaction. Or you might even think about it as sometimes reactants to other reactants. And what we recall from our work is we recall that chemical quantity comes in various flavors or different kinds or amounts. And those different kinds or amounts are described by things like mole, mass, volume of gases in liters, as long as it's at standard temperature and pressure, or our different kinds of particles, our atoms, our molecules, our formula units. To organize our thoughts, I devised or created this map. And this map shows that there's always going to be a given amount, some numerical quantity that we know about already, and some desired amount, some numerical amount that we're relating that given quantity to. So reactants, things that we begin with, the quantities of those are specifically related to amounts of products that we could create. If you recall some time ago, we talked about an analogy, how if you had ingredients for making French toast setting on the counter, the ingredients really dictate or determine how much French toast you'd be allowed to make. They're related in what we would call ratios. So let's get right down to an example of stoichiometry. One thing that we're going to have to keep in mind before we get started is that the quantity type can change, and it can be any of four types, either mole, volume in liters, mass in grams, or some particle type. So here we have what looks to or appears to be a word problem, which is really what stoichiometry is, words about reactants and products. And we're looking for the given quantity. When we read the words, the given quantity is always a numerical amount. Therefore, the given quantity in this particular example is 7.65 moles of oxygen. I like to mark right on the chemical equation which chemical is given. Therefore, 7.65 is the given quantity. You're going to notice here over on the left, I placed the value 7.65 right along mole because it is a mole amount on the given side of this map. The desired quantity, it's asking about a chemical called potassium chlorate. It asks how many moles of potassium chlorate. Well, you'll need to remind yourself how you recognize what potassium chlorate is. You may want to revisit some tools that we've used throughout the year about recognizing the names of chemicals. Potassium chlorate would have the ion chlorate in it, and the ion chlorate is identified by these symbols here, ClO3. Therefore, this is our unknown or our desired. Sometimes I like to call that desired quantity the X, or the unknown. And it's asking us to determine it in a mole amount. Therefore, we have a given amount in mole and a desired amount in mole. So we could think about we are going from a mole amount of given to a mole amount of desired. Now we're going to take a look at a strategy called dimensional analysis, which we've used in class already. That strategy requires the canceling of one unit of measure to allow you to turn it into a new unit. And it uses what we call factors. For example, we could use a factor of 6.02 times 10 to the 23rd to turn this mole amount of oxygen into a molecule amount of oxygen. Or we could use its molar mass to turn it into a mass amount. Or we could use the volume, 22.4 liters, to turn it into a gas volume. However, in this case, we don't want to keep it as oxygen. We want to create a new kind of chemical called potassium chlorate, but you're going to notice that it's not connected to the pathway over here to the desired amount. So what we got to do is we got to construct a pathway. Some people like to call it a road or a bridge. And that road or bridge is going to connect those. That road or bridge that we're going to connect is given a term. The term that we call it is called mole ratio. So we're going to think about there being a mole ratio that relates the given quantity to the desired quantity. Okay, so we're going to use the strategy that we call dimensional analysis. That particular strategy, whenever we use it, the first thing we would do is write down the given quantity. What we want to do is we want to write it in a fraction bar to make it look like it's a fraction. Every time that we add a step using this procedure, we're going to use a fraction, and the fraction acts like what we would call a conversion factor, allowing you to cancel one unit or one kind of quantity to turn it into a new quantity. One thing to keep in mind is the quantity you're turning it into actually becomes the numerator, or the value on top in the fraction. The quantity that you're getting rid of or canceling typically becomes the denominator. So since we're trying to move, in this case, from the given quantity called moles of oxygen over here to the given quantity, or excuse me, the desired quantity called moles of potassium chlorate, we're going to use a factor that uses the mole ratio correctly. On the top, we're going to place the desired quantity, what we would like to turn it into, in this case, potassium chlorate, KClO3. On the bottom, what we're getting rid of or disposing of, oxygen. So we set up the mole ratio in this fashion. When we look where we get this from, we get this from the coefficients. The coefficient of 2 belongs to potassium chlorate. So we make the mole ratio 2 potassium chlorate moles for 3 oxygen moles. Again, what we're turning it into goes on the top, potassium chlorate. What we're disposing of or getting rid of goes on the bottom. This allows us to cancel out oxygen, moles of oxygen, and turn it into moles of potassium chlorate, which is really what we want for this problem. We want the amount of potassium chlorate. We've arrived at what we need. Sometimes we might call this particular example of a problem a mole-mole problem, because we started with a mole amount of given, we ended with a mole amount of desired. What we do next is we do the mathematics that allows us to determine or calculate this amount. So anytime in our factor that a number is in the numerator position on the top, it becomes a multiplier, 2, or on the bottom, it becomes a divisor, 3. So 7.65 multiplied by 2 divided by 3 becomes the value 5.10 moles of potassium chlorate. Since this is a mole-mole problem, it only requires a single step to go from mole of given to mole of desired. This is how we would solve this problem using the strategy called dimensional analysis. The second strategy that some students prefer is a strategy that I like to call the ratio proportion method. In the ratio proportion method, the thinking is similar. What we do is we write down an initial fraction. That initial fraction has the given amount on top, 7.65 moles of oxygen, the desired amount underneath it. It's called ratio proportion because two fractions that are equal to each other are called proportion. So we write a second fraction. The second fraction that we write has the identical labels as the first fraction, the given amount over the desired amount. Therefore, if it says mole of oxygen on the left side, when we rewrite the fraction on the right side, it should say mole of oxygen. On the bottom, it should say mole of KClO3. Proportions work this way. Therefore, they will be proportional. The values that we substitute in that go with these labels then become the mole ratio. So whenever we use the ratio proportion method, we will also always use a mole ratio. Those will come from the coefficients. The coefficient of 3 for oxygen, the coefficient of 2 for potassium chlorate. Now we recognize that we have what's called a proportion. Whenever we have what are called proportions, what we do is we cross multiply. So we would multiply 3 times x. Multiplying 3 times x produces a value of 3x. So 3 times x becomes 3x. 7.65 times 2 becomes 15.3. We now rewrite our problem as an equation. 3x is equal to 15.3, and that would allow us to solve for x. To solve for x, we simply divide each side of the equation by 3. In doing that, we find out that x becomes the same value as we got with the other method, or 5.10 moles of potassium chlorate. Either method actually uses the same mathematics. It's really just organized in a different format. Let's take a look at a second example of this. Okay, so we have a given and a desired once again, and we're reading, and we're looking for our given. In this case, our given, it says, is 2.7 moles of dinitrogen monoxide. So dinitrogen monoxide would be represented by this chemical right here. So 2.7 moles of that, we're relating a mole amount to another mole amount. It asks for how many moles of carbon dioxide are produced. So carbon dioxide happens to be this chemical. So please don't be confused by some of the extra information in here. It says completely reacts with excess carbon disulfide. That basically tells us there's plenty of this reactant called carbon disulfide present to allow this reaction to act completely. It's not giving us anything specific that we need for our chemistry or our stoichiometry calculation. So it's almost like we can ignore that statement. Getting back to what we do to set up our dimensional analysis again, we write down the given quantity, the number of moles of N2O. Next, we think about, well, how do we go from moles of given to moles of desired? Just like we did before, there's that road that's missing right here. That road, we like to call that our mole ratio. So we're going to use the mole ratio to turn 2.7 moles of N2O, or dinitrogen monoxide, into some quantity or mole amount of carbon dioxide. Recall, we're starting with mole amount. So mole amount of given, we're trying to turn into mole amount of desired. Mole ratio is what leads us or brings us there. So what we'll do is we'll look for our coefficients, and what we're getting rid of will go on the bottom. What we're turning it into, carbon dioxide, goes on the top. And we end up canceling out what we began with, called our given, dinitrogen monoxide, and turned it into our desired, called carbon dioxide, by using the mole ratio. 4 moles of carbon dioxide for every 8 moles of dinitrogen monoxide. This provides the bridge or the path to lead us to the desired chemical. The calculation now will determine that this is now a new chemical. It's no longer dinitrogen monoxide. It's now a mole amount, but a mole amount of carbon dioxide. So our mathematics becomes 2.7 times 4, because 4 is a numerator, it's on top. Divide by 8, because 8 is the denominator. It becomes a divisor because it's on the bottom. 2.7 times 4, divide by 8, becomes 1.4 moles of carbon dioxide. Let's look at this particular problem using the other strategy called ratio proportion. Similar thinking, we set up a fraction with a given quantity, dinitrogen monoxide, over a desired quantity, moles of carbon dioxide. So our quantities are clearly labeled as moles and moles. Again, we might think about this as a mole-mole style problem. We're beginning with a mole amount, and we are finishing with a mole amount. On the right side, we make the labels match. If it's moles of dinitrogen monoxide on top, it better be moles of dinitrogen monoxide on top again. So our labels match on both the top and the bottom for the quantities. Next thing we do is we cross multiply. That would allow us to turn this into an equation. So we multiply 8 times x. 4 times 2.7. In doing that, it turns into an equation. The equation becomes 8x is equal to 10.8. We can solve for x now by dividing each side by 8. And lo and behold, we get the same value from the other method, 1.4 moles of carbon dioxide. It matters not to me which strategy you choose. They're both very good strategies. They're both very effective. It's simply going to be a matter of your preference, but I'd suggest that you choose one and stick to it, as confusion can easily occur if you start to use both interchangeably. Okay, let's take a look at a little bit more complex problem. Process is going to be very similar. In this case, this is not mole-mole stoichiometry. Again, stoichiometry can relate to any type of chemical quantity. It does not have to be a mole amount. It'll always relate to a mole amount, however. Again, we could visualize that there should always be this bridge here, and we recall that bridge is called mole ratio. That leads us from mole amount of one chemical to mole amount of a new chemical. So let's get started with the process, thinking about what is given. In this case, it says there are 47.5 grams of dinitrogen monoxide. So our given quantity, we're going to mark that. Except now it happens to be a mass, not a mole amount. If we look over here on our map, mass is up here. It's not down here where we were in previous examples. What it tells us to calculate is a mass of nitrogen. So we're going to go from mass of a given chemical to mass of a desired chemical, which would be down here where the red X is. In order to get from mass of given to mass of desired, now this is going to require multiple steps. In this case, we have a mass of a given chemical, but the only way to turn that chemical into a new chemical would be to relate the mole amounts. So before we can really get started, we're going to have to turn mass of given into mole of given. So dimensional analysis, we write down the given quantity, 47.5 grams of dinitrogen monoxide. What we think about then is, how do we turn that given quantity in grams into the mole quantity of dinitrogen monoxide? Well, we use what's called the molar mass. The molar mass happens to be 44.02 grams when we factor in there are 2 N's and 1 O. What that does is this now creates the amount in a mole amount, or a mole quantity. So that would lead us to a new position on our little map. That would actually lead us now to knowing this mole quantity. But notice it's still the chemical called dinitrogen monoxide. We really want the chemical known as nitrogen. So in order to jump from dinitrogen monoxide to nitrogen, we have to relate what we call the mole ratios. So we'll go to the balanced equation and we'll find the mole ratios. What we want to turn it into is nitrogen. It goes on the top. What we want to get rid of is called dinitrogen monoxide. That goes on the bottom. And we plug in the coefficients where they belong. 8 moles of dinitrogen monoxide for every 8 moles of nitrogen. That allows us to turn this into a new quantity. The new quantity is now what we would call moles of N2O. So we would now be right here in this position on our map. That's going to allow us to think about what we need to do in our last step. It asks about a mass, not a mole amount. We just simply now have to realize what we do to take a mole amount and make it a mass. Well, we apply the molar mass of any chemical to do that. The molar mass for nitrogen, the gas called nitrogen, happens to be 28.02 grams. And applying that allows us to determine the last step of this. We get rid of our mole amount, and we notice we end up with a gram amount over here, mass. Mass is where we wanted to end this particular problem. Now what we can think about is the mathematics that arrives at the answer. So we take 47.5, because 44.02 is on the bottom, it becomes a divisor. We multiply by 8, we divide by 8, we multiply by 28.02. You could have simply skipped this step by multiplying by 8 and dividing by 8. I chose not to do that so that you could see that I clearly used mole ratio. We're going to arrive at a value of 30.2 grams of nitrogen from the dimensional analysis method. Let's take a look at our ratio proportion method. This is going to look slightly different than the last example, only because this is not a mole-mole problem. This is what we would call a mass-mass problem. And in mass-mass, we don't have a single step, we have multiple steps. So again, we write down our given over our desired, our given 47.5 grams of dinitrogen monoxide, our desired X grams of nitrogen. Our second fraction, the labels match exactly. You're going to notice that I already have numbers plugged in here. These numbers represent the quantities equal to 1 mole. If it were a gram amount of dinitrogen monoxide, the quantity equal to 1 mole is 44.02 grams. If it were a quantity equal to 1 mole for nitrogen, the amount would be 28.02 grams. So we always write the quantities equal to 1 mole. Next, we have to factor in the mole ratios. So we're going to use the mole ratio of 8 for N2O because N2O has a coefficient of 8. We're going to use the 8 coefficient for N2 or nitrogen because that has a coefficient of 8. So there's an 8 to 8 mole ratio. By placing them here in red, it just highlights for you that we've used mole ratio just like we did down here in dimensional analysis. It just looks different. Now we have our proportion set up. We cross multiply. So now it's going to be 8 times 44.02 times X, and 8 times 28.02 times 47.5. When we do that, we get an equation. The equation looks in this form. We would divide each side by 352.16, and lo and behold, we end up with the same answer using the different strategy. We might call this a mass-mass problem because we started with a mass and we finished with a mass. Stoichiometry really doesn't need to be forced into those categories like I'm talking about, but if you think about each individual example that way, it sort of organizes in your mind what you're really trying to do. And I like to kind of talk about that with students or learners as we go through this. Let's take a look at another different example. In this particular case, now it asks for a volume amount. Volume is still a chemical quantity, it's just not a mass. So this particular example says if 257 grams of HCl completely reacts, what volume of hydrogen gas could be produced? So we're going to mark up our given, this reactant here called HCl, and our desired, this product here called hydrogen gas. So we're going to be starting with a mass amount, but finishing down here with a volume amount. So we might think about this as a mass volume problem. Recall that in order to go from a given quantity or given kind of chemical to a desired, we always need this mole bridge or mole road connecting the pathway to go from given to desired. So keeping that in mind, first thing we'll do is we'll write down given quantity, 257 grams of HCl. Since we're starting with a gram amount, we're going to need to be able to turn that into a mole amount so we can use that information later. The molar mass for HCl allows us to do that. So there are 36.46 grams of HCl in every 1 mole. What this does is this allows the grams of HCl to be converted into a mole amount of HCl. That would place us in this position now on our map. Next, we want to go from mole of given quantity to mole of desired quantity. That is always the mole ratio step. So we're going to look for the mole ratio, the coefficients, and we're going to put the desired quantity on top, what we want to turn it into. We want to turn it into hydrogen, that's our X. We're going to put our given quantity, what we want to get rid of, on the bottom, what we started out with, HCl. So our mole ratio is 1 to 2. We place the coefficients in there accordingly. That would now bring us to a new place on our map. Now we would be sitting at knowing what a mole amount of hydrogen gas is. Since we don't really want the mole amount, we want the gas volume, we know we have to add another step. To go from mole to gas volume, you'll recall that there's a specific amount of gas volume equal to 1 mole, assuming that the gas is at standard temperature and pressure, which is kind of an assumption that's missing in the words above here, but we're always going to make that assumption in our work, that the gas needs to be at standard temperature and pressure to understand that quantity. So knowing this, there are 22.4 liters for every 1 mole of HCl. What we're then going to do is we're going to add this factor to it. What this does is this will cancel out or get rid of our mole amount, and it will turn it into the liter amount that we're interested in. Looking at the mathematics, 256 divided by 36.46. Notice I didn't multiply by 1, because if you multiply by 1, it doesn't really change anything. So we skip the ones when we're dealing with ones in dimensional analysis. We divide by 2, we multiply by 22.4, 78.9 liters of hydrogen gas. Let's look at our ratio proportion method. We start by writing our given over our desired, given grams of HCl, desired X liters of hydrogen. On the right side, we match by writing the quantities of grams of HCl equal to 1 mole and liters of hydrogen equal to 1 mole. A common mistake here would be to try to use the masses of each of these. Since we're interested in a volume of H2 or hydrogen, the label is liters and not grams. We need to pay attention to that detail. It's a common mistake that learners make when they have less experience with stoichiometry. Again, these are the quantities equal to 1 mole. Now we go back to look at the balanced equation to see if we have 1 mole of each of these. For HCl, we see the coefficient is 2. So we're going to add the multiplier of 2 for HCl. For hydrogen, we see there is no coefficient, so there's an assumed multiplier of 1. I'm just going to place it in there so you see that we considered it. You can sort of ignore it, but because this is an instructional video, I want you to see that we've looked at the coefficients. Next, we cross multiply. That turns this into an equation then. We multiply 2 times 36.46 times X, 1 times 22.4 times 257. That reveals an equation. We divide each side by 72.92. And once again, we get the same value that we got from the dimensional analysis method. The ratio proportion method, once again, is the same mathematics, simply organized in a different format. I think it would be wise to get out a sheet of paper or some kind of scratch paper and choose a strategy now to solve an example of stoichiometry. Choose either dimensional analysis or ratio proportion. Which one seems to make the best sense to you? Take a moment to see if you can come up with an answer. I'll demonstrate it here in a moment for you, but I'd like you to just take a moment to see if you are beginning to process this. Okay, so what you did is you read for the given amount, 2.95 liters of hydrogen. Hydrogen happens to be this product. You read for the desired amount, right? The desired amount asks for a mass in grams of magnesium. So in this case, we're going from a given quantity of liters of hydrogen to a desired quantity in grams of magnesium. Keep in mind, if you're using dimensional analysis, to change from one chemical to a new chemical, we need that step called the mole ratio. So let's get started. We write down our given quantity, 2.95 liters of hydrogen gas. We turn our given quantity into a mole amount. Be careful here, since our given quantity is a liter amount, in order to turn liters into moles, we have to use the factor 22.4 and not the molar mass of hydrogen gas. Some students are tempted to always want to use the formula H2 and determine how many grams. Since it specifically lists this as a volume quantity in liters, that would be incorrect to do that. That would lead us to this particular portion on our map called mole. Now we know the mole amount of hydrogen. We want to turn it into the mole amount of the desired chemical called magnesium. In order to do that, we use the mole ratio. There is a ratio in this case. I believe the ratio is incorrectly marked on here. So we're going to change that, and we're going to make that quantity a 1. There we go. I went back and cleaned that up a little bit. So now what this does is this now leads us to the mole amount, or the mole amount of magnesium, which is the desired chemical. We got rid of the hydrogen. We're turning it into the magnesium. And now that we know the mole amount of magnesium, we can turn that into any quantity that we're interested in. In the words, it happens to say we're interested in mass, so we're going to turn it into a gram amount. So we use the molar mass for magnesium, 24.31 grams, to do that. The mathematics would be 2.95 divided by 22.4 times 24.31 equal to 3.20 grams of magnesium. You're going to notice that the mole ratio was 1 to 1 in this case. No coefficient in front of magnesium means 1. No coefficient in front of hydrogen means 1. Let's take a look at the same example from ratio proportion method. So we write our given and our desired, including the quantities, the liters of hydrogen and the grams of magnesium. On the right side, our fraction matches. On the right side, what should appear there are the quantities equal to 1 mole, 22.4 liters of hydrogen, 24.31 grams of magnesium. Remember, if it's liters on the left, it better be liters on the right. If it's grams on the left, it better be grams on the right. So the labels on the top match each other, the labels on the bottom match each other. The next thing we do, we apply the mole ratio. Well, the mole ratio happens to be 1 to 1 because of the coefficients here. So it's sort of like we ignore that, but I wanted you to see that it's actually part of every problem. So now we cross multiply. We multiply our x times 1 times 22.4, our 2.95 times 24.31. We turn that into an equation, divide each side by 22.4. Beautiful. We get the same answer that we got with the other strategy. So I've provided here a number of examples of the different styles of thinking about what we call stoichiometry. 2 strategies, one called dimensional analysis, one called ratio proportion. Feel free to choose a strategy that works for you. However, I feel like these are really, really good organized strategies. And if you're consistent about the use of them, you'll develop very good, efficient skills with the process called dimensional analysis. Or if you prefer, the process called ratio proportion. In either case, the mathematics are identical, they're just organized in a different format. I hope you found today's lesson useful, and until the next time, we'll talk to you soon.